All right, so the last two reactions we're going to talk about are kind of their own little special thing. Of course, we're still talking about aldehydes and ketones, but that's going to be the Wittig reaction is going to be the first one we're going to learn about in this lecture, followed by the Baeyer-Villiger reaction, okay? That's going to be our second one. So first of all, the Wittig reactions, they take place between an aldehyde or ketone and this crazy looking guy here. So let's just pick this apart real quick. Notice that we have a carbon and a phosphorus bound together. The carbon's got a negative charge. The phosphorus has a positive charge. Really, I mean, this pair of electrons can come down here. The bottom line is that that carbon is a really good nucleophile. It's got that partial negative charge. And your phosphorus has 3 phenyl groups or benzene rings sticking off of it. So this is this big ugly thing. This is called an ylide. We'll see that in a second. Let's just take note about what happens to our aldehyde or ketone when we react it with this compound here. Let me get rid of some of my markings. Is we have the formation of this compound here. Notice that we've completely replaced our carbonyl oxygen, and in particular, we've replaced it with the carbon half of our Wittig reagent, our ylide. Okay, so same thing down here. What would you expect for the product? Again, taking this carbon from our ylide and completely replaced that ketone oxygen, leaving us with an alkene. Again, so this is what's called the Wittig reagent. Wittig is obviously the name of the dude who first came up with this. The Wittig reagent is something we call a phosphorus ylide, Y-L-I-D-E, ylide. And these are the 2 resonance structures. To be honest, I don't know why your book picks this one as the dominant one. I certainly think of this one as the dominant one. Nonetheless, you have these 2 resonance contributors that illustrate nicely that this carbon has this negative charge, or it is otherwise a really good nucleophile. I'm not going to make you know the mechanism for these Wittig reactions. I'm pretty confident that it's not going to be on the ACS exam. Let's talk about how you prep your Wittig reagent. Okay, so first you put in phosphorus triphenyl, I guess, followed by butyl lithium, and we'll see exactly what that is in a second. Basically, it's about the strongest base that you could possibly have. And that's what gives you your Wittig reagent, right? Again, just both resonance structures are drawn. But we're going to synthesize that from an alkyl halide. So first step is to toss in your triphenyl phosphorus. That phosphorus acts as a nucleophile and does a substitution reaction, kicking off that halogen. That leaves you with this here. Now you have to you got to deprotonate that carbon, and you're going to do that by using, that creates a phosphonium salt that you're going to have to deprotonate, and you're going to do that using this incredibly strong base right here, butyl lithium, where notice here you have basically it's a butane that's had one of its hydrogens ripped off, leaving you with a carbanion. This is about as strong of a base as you could possibly get. Okay, so that hydrogen's really hard to remove off the phosphonium salt, but once you do, you're left with your Wittig. Okay, so now let's talk about stereoselectivity with our Wittig reaction. It turns out that usually it's actually the Z alkene that's favored, or where your big bulky groups are on the same side of the newly formed double bond, right? So if we take benzaldehyde and we use this particular Wittig reagent right here, notice that our methyl group is now on the same side as that phenyl group, giving us the Z alkene. That's kind of odd. I mean, that the Z stereochemistry is almost never the thermodynamically favorable stereochemistry. So this is going to have something to do with the specifics of this particular reaction mechanism. You don't need to know it. Bottom line is you need to know that the Z alkene is favored, or the alkene where those big bulky groups are put on the same side. The exception is if your Wittig reagent contains an electron withdrawing group. Remember, we should be well versed in what electron withdrawing groups are from the last chapter. That's any carbonyl containing groups, right? So whether that's an aldehyde, a ketone, carboxylic acid, ester, etc. The nitro group was one. Sulfanyl group was one. Cyano group was one, right? Any of these electron withdrawing groups will actually change the stereochemistry of the final product to be the E stereochemistry. So now our big bulky groups are on either side of the double bond. Notice one other new one that we can add to this list is a phenyl group, right? So if my Wittig reagent has a benzene ring on it, that benzene ring can also act as an electron withdrawer, leaving me with the E stereochemistry. The last consideration about the Wittig reactions that we want to learn, that we want to know, is given an alkene, or which is then our target molecule, there's actually two different ways that we could form this, right? So let's say we're given this alkene here. We know that we're going to break that double bond. One half needs to be our Wittig reagent and the other half our ketone. But who's who, right? So we could either go where the ketone is the larger half and the Wittig is the smaller half. We'll call that route one. Or the other way around, we'll make the bigger half the Wittig and the smaller half will get the carbonyl group, right? Carbonyl oxygen. So which one is the preferred route? Remember how big and bulky this back end is, right? That's a phosphorus with 3 benzene rings sticking off of it. That's big and bulky as it is for these reactions. So you want to keep your Wittig reagent as small as possible. So that means that our preferred route has the larger ketone or aldehyde and the smaller Wittig reagent, right? So that's going to be the rule of thumb that we're going to use is always keep the smaller half as the Wittig reagent. The larger half should be the aldehyde or ketone. All right, so then if you're just going to sort of show overall, if you had to go from the very beginning in terms of forming this target molecule here, the first thing you're going to do is take your alkyl halide, phosphorus, triphenyl phosphorus, and the butyl lithium, right? That'll form the Wittig reagent. Again, importantly that we chose the smaller half to be the Wittig. And then add your ketone to get you to the final step. Okay, the last reaction we're going to talk about is the Baeyer-Villiger oxidation. Notice that this is what happens when you take an aldehyde or a ketone and you add in this guy. What do we call this? This is a peroxy acid. Remember, a really famous one is MCPBA. That's the one that they like to use a lot in the book and in the ACS exam, so you should know. These are a peroxy acid. We learned that we can create epoxides from alkenes using peroxy acids. Now we're learning that if we have a ketone or aldehyde and treat it with a peroxy acid, we get an ester, okay? Or a carboxylic acid in the case of an aldehyde, if this was an aldehyde, we would get a carboxylic acid. I'm not going to make you know the mechanism for this one, other than to say something that I had said before, and I want you to remind you of. Peroxy acids are really good at sticking an oxygen between an existing bond, or that. Really good at sticking an oxygen between two atoms that are bound together, right? So this carbon and this hydrogen used to be bound together. What happens is that oxygen from the peroxy acid got inserted in between it. Something that we saw similar for forming epoxides, Okay, so that's the essence of these mechanisms. You're sticking an oxygen between in the middle of an existing bond. If you were to use a cyclic ketone, then you would be sticking your oxygen between these two existing carbon-carbon bond, forming what's called a lactone or a cyclic ester. Okay, the last consideration that you have to make with your Baeyer-Villiger oxidation is when you're talking about asymmetric aldehydes or ketones. The rate of migration of the group that's being moved, right, is going to depend on this chart here. Hydrogen's the most likely to migrate, meaning easiest to stick an oxygen between. Easiest to stick an oxygen between a carbonyl carbon and a hydrogen. Between a carbonyl carbon and a tertiary carbon would be the next one. Secondary or phenyl, then primary. And lastly, the least likely to migrate would be a methyl group. All right, so let me show you sort of what I mean by this and how we would go about this. We have this asymmetric ketone here, okay? What I'm gonna do, right, so I don't know if my oxygen's gonna go here or if my oxygen's gonna go here. That's what I'm trying to figure out, all right? So what you're gonna do is you're gonna sort of erase that bond where that oxygen was and classify your carbon as either primary methyl, primary, secondary, tertiary, phenyl, or if it's a hydrogen. In this case, this would be a secondary carbon without that bond. Okay. And if instead I stuck it over here, getting rid of this bond, that would just leave me with, this is a CH3, that would be a methyl. Okay, so if I put my oxygen here, what would be migrating would be a secondary carbon. If I put my oxygen here, what would be migrating would be a methyl carbon. Which one is more likely to migrate? The secondary carbon. So my oxidation product that I would expect has the oxygen stuck in that pink position, right, between those two carbons. I've inserted a new atom. Do the same thing over here. Use different colors. I can either insert my oxygen there, or I could insert my oxygen here. Again, how am I going to choose? I'm going to go and imagine that I erase that bond. Well, that would mean that what would be migrating is a phenyl group. Or I can stick my oxygen here, erasing this bond. What would be migrating? That would be a hydrogen. Okay, so again, phenyl group. If I stuck my hydrogen there, I don't remember what color I used. Or a hydrogen would be migrating if I stuck my group there. So what's going to win? In this case, it's the hydrogen. So my compound that I would get would be this, right? Where my oxygen is stuck between that carbonyl carbon hydrogen bond, creating a carboxylic acid, right? So up top, I created an ester. The bottom, I created a carboxylic acid. Just depends on whether you start with a ketone or an aldehyde. Okay, but that's what this migration, this chart right here is sort of the important thing to remember for these particular types of reactions. We call this the migration rate. I don't really love that word, but that's what the book does and everybody calls it. And again, it's essentially, where is it easiest to stick that oxygen between? Easiest is to stick your oxygen between a carbonyl carbon and a hydrogen. That's the highest migration rate. Hardest is to stick your carbonyl or your oxygen between a carbonyl carbon and a methyl group.